Hello, I'm audible, right?
Yes, Advait, you are.
Yes, okay, thank you. A warm evening to everyone, um, and welcome to the first session of Synthon, which is the first general discussion session of Valence, the Public Journal Club. I am Advait Kulkarni, and along with me as a moderator today is Sanjay Agarwal. We are fourth year BSMS chemistry major students at IISER, and we'll be discussing this catchy title today, chemistry sus or tenable. So basically we'll be discussing the complex topic of sustainability in chemistry. So before we begin, we are very excited to have Dr. Sayam Sengupta among us today. Dr. Sayam Sengupta is the associate professor at DCS, Department of Chemical Sciences, IISER Kolkata. So he heads the BICAM lab, in which the major part of research that takes place is based on bio-inspired catalysis and biomaterials. So once again, welcome you, sir. So I'll put forward the modalities of this session. So we'll be me and Sanjay will be giving a short 10 to 15-minute presentation as an introduction for the attendees, and then later we'll open the session for discussion. In the meanwhile, if you have any questions, you can use the raise hand feature of Google Meet, and you're always free to use the chat feature also. Okay, at any point of time, you can write in the chat, and we'll discuss it in the due course. So I guess we're good to go. Sanjay, on to you.
Sure, thank you, Advait. So I'll start this little premise or the introduction to the session. So humans have thrived with nature for a very, very long time, and we have exploited the resources it provides, much like every other species does. In fact, humans have been using chemical technologies like metallurgy, tanneries, or mining for ages. In fact, and I was quite surprised to find this out, that the first sort of usage of explosives was reported to be in 10th century in China, and these explosives obviously contained nitrates and sulfates, so potentially what we call now as polluting components. But yet no issues were observed back then. So uh, we'd like to begin with the question of what has changed over the past century and a half that we're hearing all this fuzz about the destruction of nature and yeah, all these issues going on. Why is everybody so serious about this issue right now? So yeah.
Okay. So the problem lies in the scale of the things. Now, to see how things blew up to this large scale, let's go back to mid 19th century. So by this time, people already knew uses of certain naturally available compounds, majorly because of medicinal purposes. Now, for example, quinoline. Quinoline is a great example, which was derived from coal tar, and in fact, they had set up small chemical factories in small chemical factories, which were no longer, like small laboratories. They were pretty big factories. Now, people did realize, however, that the smoke and other wastes that were coming out from the factories were harmful. Even laws were made, but they kind of hampered the growth of the industries and were thus never seriously followed.
So things followed on into the 20th century, and here the problem of pollution was actually a pretty major thing. However, to begin with, in most cases, the existence of any of this environmental damage was denied. So, like the denial was their first approach. Then, in places where it was too prominent to be denied, acceptance was achieved as a necessary evil because at this point, trying to mitigate pollution by scaling things down would have actually costed jobs and made countries and people poorer. So citizens protesting against these polluting industries were effectively being sort of blackmailed with this economic argument, and because we simply could not scale such a profitable thing down. Promises were made that innovation will actually be done and this problem will be cured, but then what actually happened was that the problem was just moved out of sight instead of actually being solved. And we basically started to trade for like less obvious things, not less evil things. Like a classic example being that the height of chimneys increased, so that the pollution in the city itself was not very obvious, but the pollution was still being done at a higher altitude.
Okay, so now modern chemistry's impact has grown from, its very old days, from being insignificant, like just alchemy stuff, to a very important, uh, like great impacts, positive impacts on our lives, such as Haber's process. That feeds half the world almost. Now, we also have some very well intended negative consequences, such as the chemical warfare and use of mustard gas during the world wars and all. However, now the problem begins when bad impacts is shown by substances that are supposed to be good. Now, a classic example here I would like to take is thalidomide, the drug. Now, this was administered to pregnant women to cure their morning sickness. But as we all know, the bad isomer, I would say, uh, did affect the newborn, and they got birth with great deformities. Now, this is a very much tragic event that happened.
So the natural question that arises out of this is that if we already know of these issues, why don't we try to resolve them? And of course, we do try to resolve them, but the problem just isn't as simple as it sounds, because anything we do to try to take care of some aspect of a problem can actually have very far reaching effects on a completely different dimension that we do not even know about. So this can actually be much better exemplified from the following example from Advait.
Now, okay, let's look into the 40-year-old biofuel program from Brazil. Okay, now what they decided to convert food stock into fuel. For example, take your corn or sugarcane and convert it to ethanol, use it as biofuel. Great initiative. So it was all renewable, less carbon intensive because it used the same atmospheric carbon dioxide in the form of carbon dioxide. Also less greenhouse gases because from crude oil we get all the sulfur dioxide, like sulfur oxides and nitrogen oxides, which is reduced in this case from the ethanol. uh, but what they did not realize were the bad effects. Now, they did not consider how huge amount of water and fertilizers were being used up, and there was this ethical issue of food versus fuel. Like, they had hunger issues at one side of the world, while here they're preparing food to convert it to fuel. This is very ethically wrong. And now the worst effect was cutting down of Amazon forests. Now, to make biofuel, they were cutting down Amazon forest. Now, the debt, the net carbon debt which was created, was so huge that it would take around 250 years for us to repay this debt. Okay, and the image that you see in the slide is from an Indonesian forest. It's almost the similar case there.
But then again, it wasn't just all bad all through. We have actually seen some success in a few aspects of environmental conservation as well. So let's take the rather famous example of replacement of chlorofluorocarbons with hydrofluorocarbons. So CFCs were a class of widely used refrigerants. You all must know that, and it was very soon found out that CFCs were actually detrimental to the ozone layer of the Earth, responsible for like the ozone layer, of course, is responsible for taking care of a lot of the ultraviolet radiation, which, if would reach the Earth, uh, would actually be extremely harmful to life. So here's a schematic of the reaction, how CFCs deplete the ozone layer by reacting with ozone. So once this came to light, HFCs were actually developed, and this is now leading to actually the healing of ozone, because HFCs, because of their weak HCH bonds, would actually decompose before reaching that high into the stratosphere, and would therefore, like, although the problem of global warming still remains with HFCs as well, the like sort of the stronger issue of ozone depletion was actually mitigated very easily with the replacement of CFCs to HFCs. This sort of schematic shows that how the ozone hole was created due to the worldwide use of CFCs, and then how it's projected to actually heal almost completely thanks to this replacement.
Now let us look at another example, which was terrible for humans, and we are discussing the example of atrazine, which is widely used as a weedicide, but it interacts with photosystem 2 of the plants, and since it is reacting with a plant protein which is not found in humans, it was supposed to have no implications on humans. But a study on frogs showed that almost 75% of also the it affects the endocrine system. Okay, and we'll get there how it affects. So a study on frogs showed that around 75% of male frogs were sterile, and around 1 in 10 converted into female frogs. Okay, so this was all because of the impact of atrazine. Now, as you can see, it was because of the forceful conversion of testosterone into estrogen with the help of atrazine. And the next image that you see here is from a single frog, and it has multiple pairs of testes and ovaries. So this is very unusual what we have seen. Also, this is not limited just to amphibians like frogs. It was also seen in case of rats. Now, uh, although first it was not accepted by the PFA, later one of the PSA scientists himself said there's a still huge amount of things we need to know about atrazine. And this study, by the way, was done by Dr. Tyrone Hayes. He's a biologist at UC Berkeley, and this is the YouTube link of his TED talk, and it's just amazing.
So now that we saw what horrible impacts that chemical could have to our endocrine system, we'll also just sort of balance that out with what we can probably call a success story of another endocrine hormone. We're talking about how we defeated diabetes. Like, maybe I'm using the word defeating very literally, but still. So insulin is an endocrine hormone that facilitates the storage of glucose in the form of glycogen, and therefore narrows, like basically keeps the blood sugar levels at a very narrow range, which means that disruption in the insulin levels could actually lead to many complications related to high sugar level, in some rare cases low sugar levels, but mostly high sugar levels. So to control this blood sugar level in the patients, actually pig and cow pancreas were used to obtain purified insulin, which could then be injected into the animals and injected into the humans, into the patients, and therefore fulfilling their insulin needs. This was very inefficient and very costly because, according to a study, approximately 2 tons of animal parts would be required just to get some 3 to 4 kgs of insulin in. However, in recent years, like insulin is being synthesized using like from bacteria using the recombination DNA technology, and this has made insulin available to the masses very easily. So with this, we actually think we've presented a few a few aspects of this issue, and we would like to end our premise here. But before leaving, we would like to just leave you all with a few questions that the discussion can start to build upon. The first one is about the quantification of these effects. So we saw that almost all of these systems we were looking at actually had both positive as well as negative impacts. And how can, an important question is like, how can we actually study these impacts and weigh them against other ones? Like, how can we weigh different processes for environmental impact? And not just environmental impact, but again, as we saw, like we cannot just scale things down at this point. So how can we also weigh those impacts against economic factors, and therefore come up with a sort of a quantification of all these hazards? Another question is, of course, why not right away? In the sense that, given that we know there are so many issues with, like, and how much dire the need is to go sustainable. So an obvious question that comes to mind is why not just devote all our time and funds to going sustainable? Of course, we cannot just just go and say ki, like we'll just do sustainable stuff from now. That is of course not possible because there are not enough sustainable techniques. And the prominent question here is why not devote more time and funds to trying to develop these techniques if the issue is so serious. And of course, given that we believe most of the people here are sort of aspiring chemists or aspiring scientists at the very least, how can we an important question could be how can we try to make the chemistry research itself greener. And yeah, because research itself is actually a very small part of all of this environmental issues, we do not know how much impact it would have, but then this is one thing that is directly under the control of chemists right away. And what simple improvements can we do to get there? This is another question we could think about. So yeah, with this little premise, let us begin the discussion. And once again, please do not speak without raising your hands first. We will ask you to speak. And you can use the chat whenever you like though, and we will read things out from the chat. Also, any doubts or comments about the presentation itself are also welcome, apart from the discussion on the general theme of sort of the greenness or sustainability that can be achieved in chemistry. So yeah, anybody yeah, please add stuff, and then maybe Sayam sir, if you could add a few things to this.
Yeah, so it's a nice presentation, and let everybody start a discussion, right? I'll pitch in if it's necessary, and I want to hear what people think, okay, and what people think about this. So and we can go from there.
Okay, sure, sir. So yes, people, if anybody wants to, yeah, Sumit,
Yeah,
please go
Sumit,
on.
go ahead.
Yeah, hello. Can you hear me?
Yes, Sumit.
Yeah, so yeah, really great presentation. Yeah, thank you for this. But what I was thinking about is you said in the end that, sustainability or, the fact that the research does not harm anyone needs, funding so that the researchers themselves can spend more time to make the entire thing more sustainable or more safe. But uh, but you said in the end that it's something in the hand of researchers, which is only partly correct, because research in itself is highly dependent on the social economic factors surrounding, say, an institution or certain country, right? So what I was thinking is, because scientists are not really so free to do as they choose, because they are bound by things such as grants. And grants are in a way glorified product making schemes, because all the grants wants us to do is make something, or have do some research that has some sort of intended product as soon as possible. And that is something what scientists don't like. Many of them don't like, right? Because we want to do science the way sort of blue sky research. But we are bound down by these deadlines and these grants. And uh, obviously that's one of the big problems that is sort of I won't say plaguing, but is an integral sort of part of the system, but also should be in a way changed, or some sort of reform is needed in that. What do you guys think about that?
Yeah, okay. So, firstly, the grant thing, like when we said green chemistry labs, and so like making the chemistry research green, we were thinking more in the lines of, say, using lesser protecting groups if possible, or using less environmentally hazardous solvents and stuff like that. Of course, like the grants thing come under this point where, like, oh, yeah, can we not devote all our sort of times and fundings and stuff onto trying to come up with sustainability techniques? So that is a different thing. That's the first point. And of course, on the grants thing, I'm really not very familiar with that. So maybe, yeah, here we do need sir to talk about it, because I do not know how exactly all this grant system works.
Okay, so I'll partly agree and partly so I think Sumit is absolutely right that it is not only about the researchers, and I'll tell you why. Because simply, so, there's absolutely no dearth of grants. Suppose you have so now these days what is happening, especially in the West, is there are many environmental regulations. Any chemical industry, if you ask them, they spend more money cleaning their waste than they even use for producing their stuff. Okay, there's something called an E factor, which says that for one, so imagine a pharmaceutical intermediate. For one kilogram of an intermediate you make, you generate 25 kilograms of waste. Okay, and that waste, earlier days you could throw it down the rivers and the oceans, but these days, in the West it's very tough. Even in some in a country like India, this whole issue with the in Tamil Nadu with starlight industry, right? The people around were very upset, right? They said that you're pouring in toxic things, and people are more aware of it, and so the industry had to be Vedanta had to be closed, right? So I think people understand that processes have to be improved. They have to be made inherently more safe. They have to be improved upon. Okay, for sure. There's no question about it. But there's also, and that is where public policy, not only research, but public policy comes into place. So, you have to have regulations in the country which says that I cannot throw the waste which I generate down without treating it. Okay, that's one part. That's one part. And again, now if you go back, so then, and this has to be enforced. It's not like what happens is, okay, there's a rule, then the inspectors come in, then you bribe the inspectors, right, and then you get away with it. So what is going to happen is, not only there has to be, not only there has to be a policy which is there, but there has to be an enabling, that's where the state comes in, an enabling place where you would be allowed. So treating, for example, by itself, by a company will take a lot of money, and so the company will think, if all this money is gone doing this, treating this waste, where is my profit going to come from? So all these are in place. So there is a role of government, there's a role of public policy, and I can give you one example. In Chennai, the leather industry was supposed to be closed because they used chromium, and this discharge of chromium was, the courts had said that they would completely stop it. And the former DSC secretary Ramaswamy, who is also an honorary professor of IISER Kolkata, they set up a very nice method where they used a natural product, to sort of sequester the chromium and make it green and saved all the tanneries. So there are good science in place, but science, public policy, okay, and the government regulations as well as implementation, all of these has to be done in sync so that these can be implemented. So it's a very complex process, and I can talk at the end why these sustainability problems are known as wicked problems, and I can talk about why these are called wicked problems maybe at the end before we finish.
Thank you, sir, for that. So in the chat, Madhur says that using metal-free techniques would be good for sustainability, and these toxic metals are a big headache for the pharma industry. And yeah, I guess we all agree. And actually, like the field of trying to make processes metal-free is actually, I guess, gaining interest. And yeah, there is actually a lot of study being done in those areas, if I'm not wrong. Subhajit says there are many CC coupling reactions, carbon-carbon coupling reactions, as well in synthesis, which use many harmful transition metal complexes. Okay, so to substitute them, research can be improved, and we need to think over this, and also use the solvent. Also, use of the solvent is a significant issue. So yeah, Subhajit is just reinforcing Madhur's point. And yeah, as for the solvents issue, of course, yeah. How, like, is there a way we can actually try to basically grade the solvents in the sense that, like, which one is more harmful or less harmful than the rest?
Yes, you can. Actually, I can forward the paper to Sanjay to show it to you. Bristol Myers Squibb had a incredibly good paper where they have categorized the solvent in terms of global warming potential as well as toxicity, and they've put some charts in, some numbers in, some quantifiable numbers in. I can circulate that paper and you can send it to interested people.
Sure, sir.
Thank you. Madhur, I guess, go ahead. You had that question.
As Tahiti said that some solvents it is difficult to do reactions and we can reuse it. But instead of that, there are some ways in which we can use mechanical techniques to do the reaction, like how we used in the mortar and pestle in second year. We can try to do mechanical techniques and do completely solvent-free reactions. That would be sustainable, right?
Yes, so as far as I know, I think the main motivation behind those reactions is the fact that they are solvent-free, so they are not just sustainable but also more economical. But then, like, there is a very limited number of reactions, I guess, which can be done using using mechanochemistry.
Yeah, it would be
And
great if we had more of such reactions, right?
that is
Solvents.
true. That is true, I guess. Yeah. So, yeah, okay, Vedant
Yes,
wants to
Vedant.
say something.
So I had a general point. I mean, I don't think it's necessarily along the line of the discussion we're having now, but another issue with sustainable reactions or sustainable alternatives coming more from a synthetic biology perspective is using or engineering bacteria or other organisms to do your job is the rate at which you want to get something done is significantly slower with the current boundaries of research that we're working with compared to using just dumping chemicals into whatever in terms of like using a bunch of chemicals to solve your problem. And the context for this is I was actually looking at, so every year around winter, January, December, there's this burning of husk that happens in northern India, which is a huge problem. And I mean, it's not a technically you don't use chemicals there, but the alternative is, can you use some other either solvent or material or anything to basically degrade the husk to, instead of just burning such huge amounts of it. And the problem you consistently run into is, theoretically, yes, you can engineer bacteria or yeast to break down the polymer chains and cellulose and you break down cross links, but it's just not nearly as fast as you need it to be. So like, I think green chemistry in it's heading in the right direction, but I feel it like lacks significantly in terms of how fast we need things to get, or how fast we need things to be. Like, it's, and I think that's a problem that if in from the perspective of course, if you have things that are, say, government motivated or industry driven research, how quickly you get something, an output out, is definitely going to matter. But even research in institutes like IISER as well, I mean, you can't neglect the fact that there is a pressure to get the job done. I'm sure like Sayam sir will be able to maybe comment more, but I think that always, that factor is is never weighed against how much time you really spend on each individual reaction or whatever you're trying to solve. It just takes much longer. I mean, long story short, it takes much longer to use greener methods than using what's the standard practice, and to break out of that convention is very difficult because of that reason. And I don't know if there's it's a comment, not a question, but I don't know if there's a method around that really.
Okay, I'll put a different spin on this. Okay, so where the discussion is going right now, and it's going on in the right direction in terms of, there was this question that it's just very slow. There are so what you have to sort of understand is, okay, so one of the problems with most if you sorry, how do I pitch this? Okay, imagine this earth, okay, and imagine we didn't have any industrialization. We were hunter-gatherers like really long ago, and there were very few people in the earth, and everything was great, right? So you had the sun, the solar energy coming in, plants where there was photosynthesis going on, oxygen being produced, we were eating plants, that was being made into different manures, and things were sort of in a not in a closed equilibrium, but in some sort of a harmony. Okay, and now we've started perturbing all of these, and what essentially has happened is we are essentially consuming way more than what is being replenished. Okay, and in all of these, what you always need to realize is second law of thermodynamics is against you. The entropy is always increasing. Imagine this: you had millions of years which took to form oil, okay, which you sort of dig out from down, and then you drive a kilometer, all this is made into CO2 into the atmosphere, never to be taken back. You see this problem, right? You take, for example, you use lithium ion batteries, right? So you take lithium, okay, from and it's not really all over the world. It's only at certain places. You dig it from those ores from certain places. Then you put them into batteries. They will be used all over the world. And after its life is over, they're thrown down, okay, and that is gone, and you can never recover. So useful energy, is always being converted into something which is so when you have one thing, one energy is converted into something else, the amount of useful energy is becoming lower and lower and lower. Okay, so that's the entropy is always against you in what happens in what goes on here. Okay, and so that is actually a huge problem, right? So what you need to find out is a circularity, right? And the way nature does it. So whatever you consume, that has to be circulated into the system rather than burning it down, like we talked about the haystacks and stuff like that, right? And that is a process which you need to which chemistry is looking at in something called circularity, the way nature functions. It used to be the photosynthesis functions, the nitrogen circle, the CO2 cycle, which you have learned in earth sciences, right? So chemistry is also to do something with materials, right, in which you sort of keep on recycling stuff. And that is essentially going to be a huge key in achieving sustainability, which is very complex. So one of the things I realized while all of you were speaking is you only talked about the chemistry, okay, that we need to have better chemistry. And I completely assure you, there are many research ideas, engineers, chemists, all trying to do better processes. But what Sanjay and Advait talked about, there are two things. One is, okay, I know a chemical which is important for our civilization, and I need to make it in a better manner. So I make less waste, I make it less polluting. The other part is, what about the chemicals themselves? That what was talked about. These chemicals were made for a purpose, and all of them had unintended consequences. You made CFCs because you wanted better refrigerants, which looked nice, but it created an ozone hole. You make an atrazine, okay, to kill pests, and that is bending your gender, okay. And there are numerous things like this. We didn't talk about PFAS. You can see the movie Dark Waters, right? There's so many of these chemicals which are coming out, which we have no idea what unintended consequences are going to be. So how do you think chemists should design chemicals which do not have these unintended consequences? That would be something which you might start considering, because that's not something which is taught in the chemistry classes. Chemistry class is all about how I do a better CC reaction, how I use a less solvent. And that is important. It's fine. That's a process. But what about the right chemical? We have all these dioxins which have problems. All of these, right? How do you design chemicals which have no unintended consequences?
Sir, on that, so even if we first of all, even if we come up with some sort of a molecule, how do we even know if it has any unintended impact or not? Because there are just too many different ways where it could interact, right?
Absolutely. How does a chemist think through it? You have to think through it. Either you have to. So I'll tell you. I'll give you a sort of a number. There are 100,000 chemicals on the market. 100,000, out of which 4,700 chemicals are used 100 tons per year. Imagine the amount. Okay. And out of which 500 are only completely characterized. We know they're good or bad or whatever it is. So how do we do it? That is something which we do not discuss, right? And this is going to be the biggest challenge for chemists. How do we ensure and tell see, now the word chemical, you go and tell outside chemical, you think it's dangerous. The word chemical is equated with dangerous. That's how our science has become, right? So how do we change this? How do we tell people that chemical is not dangerous, right? How do we make chemicals? How do we ensure that these are not going to be dangerous?
Sir, do you mean to say that after a chemical is being before a chemical is being used in industry, there needs to be some policing that ensures the sustainability of the chemical?
Absolutely. That is,
So you mean
that is
to
one word, right? Yeah,
yes,
of course,
sir.
But
Yes, sir. Yeah.
how? Not only that. If suppose I have to make, for example, I have to make a frying pan. I have to make a non-stick frying pan. I would use Teflon. Okay. Now, if you see dark waters, you will see that this comes up. Teflon is a great compound, but it comes up with all sorts of things which you're using. Okay. Now, how do I conceive making something which will not have the unintended consequences? Okay. And I'll give you a hint. There are three very big examples. And if you see most compounds like DDT, dioxins, and all these compounds, you could look into it, and we'll leave the gender bending chemicals for a little bit. These are compounds which are known as persistent compounds. They do not degrade. They stay in the environment. They do not die. Our whole nature is about creation, destruction, creation. But these chemicals would stay forever. So this is called persistence, and they bioaccumulate in your body. Okay? And they're toxic. So how do you design chemicals which do their function and they decompose into fragments which are not going to be harmful? Okay, that I think, the process which you all say is good because we teach you this, chemists and chemical engineers know this, but what is really not known is to how to understand and make chemicals and have also testing, however assays, which can tell us whether I put a chemical in the environment that is not going to create an havoc having unintended consequences. That is going to be the big challenge, which I believe, okay, a huge challenge.
Sir, so we have a few comments in the text box, and so here, first of all, Madhu says that some index should be made that quantifies how sustainable it is from like a substance is from the grassroots level and how it increases at every level of a synthetic pathway. And
okay, hold on. Wonderful. You should have a metric which talks about sustainability. Okay, wonderful. Now let me tell you what the complexity comes in. So these sustainability problems, these are known as wicked problems. Okay, because in chemistry, in science, we are only known to look at only one parameter. Okay, but these are so many conflicting parameters which make it very difficult and of course very interesting. And I'll tell you how. So the current parameter, which is looked at, which people look at quite a bit when you look at sustainability, is the amount of CO2 which is made. Why is it? Suppose you have to make, somebody talked about ammonia, right? Ammonia Hayward's process is thought to have very fed so many people. I can argue for you and share you articles which says Hayward's is such an unsustainable process. Do you know how much CO2 is produced because of the heat you need to make ammonia? Where is that CO2 going? And with all the ammonia, ammonium compounds you're putting into the fields, nearly 40 to 50% just gets simply washed off into nearby seas, and that leads to eutrophication. So what people try to do is that the index they try to do is, whenever you have a process, you look at how much energy is required, and then they equate that with the amount of CO2 which is being produced. Because we all know CO2 raises global warming. Now the question is, okay, so you have a process which says, okay, I calculate all of these. I have a metric which says how much energy, how much CO2 is being produced because I'm doing this. But now you have one process, one chemical which comes in with very less CO2, but it can have toxicity to marine life. And then the other chemical which has very high CO2 but has no toxicity to marine life. Now, how do you have a metric which is, so toxicity will have a different metric. Your CO2 energy will have a different metric. Now, how do you need to put this together? Okay, so this is where some of the real challenges are coming in, which chemists are trying to address. Not chemists, chemists and every scientist is trying to address it. Your generation needs to address this. Okay, this is way more important for you to understand how do you look at very different matrices and then come up with an idea whether this is sustainable or not. Okay.
Sir, can I ask something in this regard?
Yeah, sure.
I had read something peculiar about a particular species of bacteria that can actually digest plastic.
Right.
So rather than going for chemicals or processes that might actually reduce the amount of unsustainable waste that is produced, can we also think in the manner that we can always genetically modify organisms, or we can produce systems where biological systems that can actually break them down back into the raw materials that we started with again? So
very good. Excellent point. Okay, so
over here,
so this is a very great question. So question is that we have bugs. It was very important when the oil spill happened in the US. There were genetically engineered bugs which went and sort of fed on the oil. So why can't we take plastics? Now the question is, as a chemist, you would know that the word plastic is very loosely used. Okay, there are several different type of polymers. Like imagine, just go ahead one day, take your Lay's packet. Do you know how many different polymers are there? There are 3 different polymers, and they're very different structures. Okay, they're very different properties. And imagine we have 3 different polymers put in micron thicknesses putting together. Okay, and imagine the amount of Lay chips are made in the world. Imagine how much they're dispersed all around, and think about that. Would it be practical, as of now, okay, to have a polymer made of different a material made of different polymer layers? Maybe you need different bacteria, okay, and that needs to be shredded, put into somewhere. There has to be a separate time frame, okay. So these are challenging problems. What is done in polymer right now? There are 2 ideas which people do. People look at either recycling, okay, which is, suppose I have a polymer, I don't know, some polyethylene bumper of a car, right? And so when my bumper is broken, they try, because it's made of maybe it's made of one material, we take it, you break it down into small and then try to get back the original polymer material and remold it. This is called recycling. Okay, but then every time you do it, you lose something out. The other thing which is done is called upcycling. So you take that polymer and then you make something which is more valuable from that. So you increase the value price. It's called upcycling. Okay, but in more cases it happens in case it goes downcycling, and it's such a complex problem. Okay, so I don't like advertising for classes, but I can share with you at the end that we teach this. If somebody is really interested about polymer recycling, I have those recorded lectures from last year's class, and I could forward you. We have this was wonderfully discussed out in terms of recycling, including practical problems in polymer recycling. And if Abel, you are interested, send me an email. I'll send you those links. Those who are interested, if you really want to know what the real challenges are. It's such a fascinating problem to work on.
Sure, sir. Yeah. Thank you.
So in the chat again, Shefali mentions that the aim is of thinking of synthetic routes that require minimum energy, and
right.
So at the same time, they should also rely on non-hazardous and eco-friendly energy sources.
And also they should be not greenhouse solvents, right? You don't use carbon CH2Cl2, which are typically will which typically will form those. So yes, absolutely. So Shefali is absolutely right. These are the major parameters, but toxicity is also one of those.
So what she's coming at is that this is very similar to what happens in photosynthesis,
Right.
And therefore this recent emergence of the area of artificial photosynthesis has been gaining attention
Absolutely.
in attempt to try to use and release non-hazardous chemicals, like maybe simply water, in fact.
Absolutely.
So and then what Madhur counters this with is that most of these photoredox catalysts we have are actually relatively very inefficient.
Yeah. So Madhur, we could do it in a different way, right? So of course, you use iridium, tris-based pyridine, and ruthenium, and those are never going to be useful. Okay, let me tell you upfront. Okay, but imagine the power of the idea. Okay, so instead of shining light, and you have a sacrificial reductant, and you have a complex which sort of what does it do? All of these, this form either a strong oxidant or a reductant by using part of the energy from sunlight, right? Okay, so you could do the same thing, okay, so at the end basically it is taking energy from the light, but you could do the same thing by using a solar cell and taking energy from the light, okay, and using electricity to do reactions. So there's a lot of progress right now in electrifying organic reactions. So so essentially you want to give the energy which so imagine you heat a reaction, you flux a reaction. Where is this heat coming from? This heat is coming from either the electricity which you're using. Where is the electricity coming from? It is coming from a thermal power plant in Kolkata or Bandel or somewhere like that, right? What is this coal plant doing? It is basically making CO2. Okay, so at the end of the day, for the electricity, for every heating the reaction, you are making CO2. Okay, so now you want to stop that. So instead of that, you want to take light, you want to take the energy from the sun and use that energy to the reaction to heat up the reaction or give energy for the reaction, rather than using it burning fossil fuel. That's the very, very basic general idea. But that is what chemists are really trying, okay? And everybody's trying. So energy is the most important thing, because whatever needs to be done, driving a car, everything requires energy, because we consume more than what is reproduced. And what nature does is, nature takes diffuse sunlight and makes it into oxygen, which is incredible, right? Because oxygen is a high energy molecule. When oxygen mixes into water, it's an extremely exothermic reaction, and that is what drives life, the reduction of dioxygen into water. Now, we want to do the same thing of harvesting light, and like nature, takes water and makes it into a high energy molecule. We want to store the energy somewhere and use that energy to sort of drive our planet, okay? And that is one of the most important areas of research chemistry would do, is to find clean sources of energy, because at the end of the day, everything is linked to energy, clean energy, which does not produce CO2, okay, which does not reach to global warming.
Surajit had a question. Go ahead, Surajit.
Okay. So like I do not have a proper question, but I think Sumit is also saying the same perspective, I think. So I'm getting enlightened by all the ideas which I'm learning, and as we can see that sustainable research is thriving in many areas and will be expanding in the coming years. But an impending problem is the time scale. I mean, we know that research takes many years, and most of the research is not translated into industrially efficient processes. Now, we all know that the climate crisis is like impending.
Yeah.
I mean,
Yeah.
like I was reading recently that it is being predicted that with the current economic growth, it will be like by 2040 the economic growth will collapse. And like whatever research we are doing, since it is also economically funded and also dependent on public perception of the necessity of research and all, so like we also don't know, like we are also hit with the uncertainty of what will happen if that happens. I mean, with the economic collapse, will the public start thinking that these research are not really helpful in the like immediately, or
No,
will people
Surajit,
be enlightened?
I
I
could,
mean,
last year in our course, so there are so many great ideas people are trying to commercialize. Okay, so many great ideas, including companies which there's a company called Solar Foods. It's a startup which is saying we'll make food out of CO2. in a way which is commercial, using bioorganisms, as Abel was talking about. There are, we are undermining our human intelligence. We sent a person in the moon in the 1970s, like 1960s. Come on, okay? We are undermining ourselves. We could do really a lot of incredible stuff. I think so many. We could not even imagine that the electric car would be a reality. Look at how Tesla has come up, right? But the problems are complex. We need both research, government, public policy, and at the end us. Okay, we need to understand that we cannot consume more than the earth replenishes at the end of the day. Okay, there is something called an earth overshoot day, and some countries overshoot, like, whatever the earth gets back in a year, in how many days we are actually utilizing it, and every country overshoots it. Countries like Qatar and all overshoot it by February, it's done. Whatever the earth gives them in 2 months, they're consuming it within 2 months. Okay, so it is also to be us as a society, the government with its public policy, and scientists, okay, and social scientists who understand it doesn't have to be a policy. Policy has to be also implemented. So this is what is called, this is a problem which requires multiple dimensions, and that has happened, right? Imagine we did ban CFCs and got a replacement. It did happen, right? The ozone hole was finally fixed, and we did do it. Okay, so it is a challenging problem, but I'm sure we could do it. We need to know what our problems are, and all of you need to realize that this is one of the most fundamental things we will be working in our lifetimes, especially climate change. Okay.
Sir, continuing on Surajit's note, so I was just curious if there ever will be a point of no return, so it's over.
Why do we think about doomsday? It's not yet there, right? But why do we think about it?
I mean the more realistic perception of doomsday, in that the turning points of we know that there are 7. I don't remember the term correctly, but I remember that there are 7 processes in the world that has been mapped out by environmental scientists, and they are the Arctic ice, and that I can't recall, but I mean the tipping points. Yeah, the tipping points I'm talking about.
Right. See, I'll give you a counter example. Look at from 1970s. They said that oil is going to be finished in 20 years and we'll have doomsday. Did it happen? You can keep on seeing this. They will every time keep on saying, okay, coal is going to go in 100 years, oil is going to go in the next 20 years, right? And of course, so it is not the doomsday is so near. I think we have it into us to solve this problem. Okay, and I'm sure this problem will be taken care by people. If most people are married into it, this is going to happen.
Yes.
So maybe I'll do a little bit of advertisement because it's already nearly 7 o'clock, so everybody will go. So from last year, we are teaching this class called Chemistry and Sustainability. Sorry, Sustainability and Chemistry. Okay. So this is being taught by myself and Dr. Shivaram, who is a very famous person. He is currently in Pune. So thankfully, it's all online. And so this year, we are also doing this. I could, could I present and show what we are going to teach this? We just fixed our syllabus, what we are going to teach this year. So those who are interested, if you're really interested into this, we are going to talk in excruciating details about a lot of these things. Okay. If Sanjay and I really don't want to publicize this.
It's fine.
Like publicizing courses and all, but I can tell you what we are going to teach. Okay, and if these are of interest, you are welcome to register. You're welcome to audit. You're welcome to sit for any lectures, because I think this is an important topic. We will post all what topics we are going to have Tyron Haynes come and give a guest lecture. We're going to do a lot of things, but I want to tell you what we will do, and you need not you take this class, but if you're interested in one of these topics, and because a lot of this will be standalone topics, okay, you are welcome to sit down for these lectures. Okay, we have quite. So with your permission, can I show this
Yes,
syllabus?
sir.
Yes, sir.
Yes,
Yeah,
sure.
yeah, sure.
Okay, can you? Okay, so
Sanjay, stop presenting.
Yes, sir. Just a second.
now what is the problem? Why can't I get this Excel sheet shared? Hold on. Okay, probably I need to do the entire screen. Hold on, just a minute. I'm a little challenged today, so let me see. Screen. Can you see an Excel file?
Yes, sir.
Yes, sir.
Yes, sir.
You can see the Excel file, right? Okay. So I'll go through quickly what we are going to do. Okay. So we have the unit, okay, and what we are going to teach. So we'll start with, what Sanjay and Advait started with, putting into perspective that how did we get here, okay? And we talk about what is sustainability, and I talk to you why this is a very complex problem, and the principles between need and greed, greed because we are always greedy about many things. So we'll have an introductory 3 lectures setting up the scene. Then we'll talk about, that how we can learn sustainability in biology, frugality and circularity is nature's design. For example, synthetic, carbon dioxide cycle, nitrogen cycle, water cycle, and these examples, how we can use to have this circularity in our world where materials which we are taking from the earth, we give it back there and not let it, we keep on reusing it and not putting it into the ocean or somewhere else. Okay. After that 2 lectures, we'll get into something which somebody discussed. How do we measure circularity? And we'll talk about carbon footprint, something called a life cycle analysis, right? So suppose I think about a silicon solar cell, all these CO solar cell. So we start about, okay, solar cell is it sustainable? Because you have to start about how are you making the silicon? From what is the process? How much energy is required? To how you dispose it, right? From the birth to the cradle, right? We look at the whole process and we'll try to explain how you sort of understand whether the process is sustainable or not. So once we are done with this, we look at the current challenges in sustainable science, which we discussed today. One is how do we design? So what are the problems with some of these chemicals with this unintended consequences? And the other one is the inherent safety with chemistry, right? That we have all this Bhopal gas leak and all of these issues which we have in chemistry. So from there, we will get into a little bit about climate change, okay, talking about the problem with CO2. And then we'll also talk about the science behind carbon capture. So one of the big ticket issues which has been tried in the industry and in academia is that, so from all these industries, when CO2 goes out, can you get a technology which can trap this CO2? Okay, and what are the challenges, okay, with associated with such kind of issues? So from there, we'll get into energy, which is the biggest thing. So there are going to be 6 lectures, and we'll only look at the renewable energies, that is hydrogen, solar cells, and fuel cells. Okay. After that, we'll look at water. Water is a huge problem, right? Drinking water is what access to good, clean drinking water is a. There are people from Maharashtra, and I'm sure I was in Pune, so I would know people in Lapur and all these places how difficult it is to get clean drinking water, right? So the issues with water and what are the challenges. So from that, we'll get into green chemistry, which today talked about. And I will talk both about designing chemicals so that will not have potential to impact environment and those living in it. And then also how you have clean processes like solvents and what we talked about. So that is going to be one part. Then we'll do a part on sustainable plastics and rubbers. And we'll talk about the whole plastic issue. How do we recycle plastic? What are the challenges? What are the newest challenges about recyclability? How can the reason I'll give you an example. The reason you have this very fancy 3 polymer layer of a lace packet, because single polymer cannot do this. But how if we had a single polymer which give you the same function as what is required in a lace packet, then you can easily recycle it, right? So we're looking at, we look at the science, we look at the engineering, we look at all of those. Then we'll do a lecture on, we have all these rare earth metals and lithium and all of these, you use, imagine a solar cell. You know how much silver you use? We use very little amount of silver, and the whole world silver is going down because we are disposing it off. So how do we understand? So we use all this trace amount of metals in all our electronic gadgets, and we never recover it. So this is what I was saying, right? The entropy is completely against you. You are digging it up from a mountain. You're extracting it. Then you're making zillions of this equipment and then throwing it away, right? So how do you think even about reusing or recovering metals from waste products? Okay, we won't have time to do agriculture, but I will finish up with something which is economics, which is very important. At the end of the day, it is about economics. If it is not economically sustainable, there will be no takers. So how do we, right now, when you sort of use a land to cultivate something, and the land quality goes down, you never count it into the price of your crop. Okay, but how do you build in such indicators into when you manufacture, right? When you have agriculture and other things. And at the end, we'll talk about public policy and the need for societal change. So that's going to be our class. Okay. Again, I don't want to advertise courses. I don't like it. Okay. I will share it with those of you who are interested, which day we are having what classes. We're going to have very special experts coming and talking about various topics as special classes. This is a 5th year class, okay, 5th year course, which we are doing this year. We have done it last year also. So if you're interested, you're welcome to take this course. If you're just interested in sitting and listening to some lectures, absolutely welcome, okay, to a special lectures. I want more and more people to think about these topics because these are going to be really important. Okay, so that's again, I just want to make it clear that this is not, I'm not advertising this course. Okay, I just wanted to say what we are going to do because this has been the topic today, and we are going to do a lot of these topics in excruciating details. Okay, in talking about the real factors and how this is such a complex problem. In a chemistry lab, you're only thinking about, okay, how do I improve the yield of this reaction, or how do I change manganese to an iron to do a reaction? But the real world problems are so cool because there are so many things to putting it together, right? And you will get a flavor to how these things work out. So for those of you who are interested, okay. So I wanted to give you tell you this, but I will also put down these lectures. They will be also video recorded, and I'll also give you the date. So you're welcome to join in any class you want and ask questions if you're interested in any of the topics. Okay. Sanjay and Advait?
Yes, sir. Yeah.
Okay, so just wanted to.
Yes, sure, sir.
So,
So, okay, by the way, so we have, like, I just received a question from a friend.
Yeah.
She's asking that she actually did not have chemistry in a pre-major level, but she still wants to.
Doesn't require chemistry at the pre-major level.
Actually,
course
the
does
course
not
page
require.
listed. No, the course page on the teaching plan actually lists this as a requirement.
I will check into it and actually send me an email and I will allow. You really don't require a knowledge of chemistry. I think whatever little bit is required there. So last year we did much more of chemistry we thought, but this year we are completely redesigning it. We just had a meeting and we are still putting it together. But it would not require this. It doesn't require a major. It doesn't require a pre-major. You would be fine without, if you know a little bit of thermodynamics, a little bit of chemistry, +2 and a little bit of first year chemistry. If you remember some of those reactions we taught you and all, this is more than enough. I think this is fine. You don't require much inorganic chemistry at all. What we require maybe a little bit of thermodynamics and all, which you have done. So this is going to be fine. And the green chemistry part is also going to be straightforward. And if there's a little bit of help required, we'll give you that help. So send me an email if you don't have the pre-major, and I will write to DOA and I will allow it. If you're interested, of course.
Yeah.
Okay.
So,
but you don't need to. But you don't need to credit this. You can always audit it. You can always sit in any of the lectures you want. Okay. We just want you to know these topics because this is not taught. And we really want you to at least get out of IISER knowing some of these issues. which we'll talk about.
Sure. Thank you very much, sir. So, when you were showing the course details, one sort of discussion that was going on in the text box was about whether there is an overestimation or an underestimation of the, say, the climate crisis. Because while on the one hand, like in the 70s or 80s, like 60s, 70s, it was said that maybe like by 1990s or 95, we would actually have already exhausted most of our resources.
Right.
And
Right.
on
No,
the
so,
other
so,
hand, like there are studies now that show that we are actually underestimating the issue. And when we put forth a line on 2040s, for example, there are studies that say that this might actually be like maybe nearer than we are thinking. And so, like, how do we make sense of that?
So yes, absolutely. And we talk that in our class, right? That we teach that in our class, that how the goal line has been kept on shifting, So there was this very famous from Malthus, which said that, the population, what is going to happen, we are going to grow over the population and there's going to be a food crisis, and all these things. So we talk about this in our class, okay, about these issues. The climate crisis, for most, I think any practicing scientist would tell you it is real. We are, there are these pictures from Antarctica, which is coming very recently, right? For all the ice that is getting melted. Well, do you know this year I have lots of friends in the US, in California, the temperature went to 45, 46 degrees Celsius, unprecedented amount of temperatures. So I think the climate crisis is real for sure. At least that is what the thinking for all practicing scientists. And there has to be a way to bring down the CO2, okay? And this is going to be one of the greatest challenges we have, okay? And chemistry has to play a humongous role into this, into how we, actually we do a lecture in which we say that when oil finishes off, right? So this is also one of our chemistry lectures which we do in our class. So one of the things which you're not realizing is all the chemicals which you're using right now comes from oil, okay? And you take oil and you sort of make new chemicals. And of course, the oil keeps on, we keep on getting more and more oil. Also, there are methods in which you can take carbon dioxide and make into fuel, okay? Those are also known methods, but all these are energy intensive. So at the end of the day, it all comes to energy, okay? We actually do a lecture where we say that CO2 can be used as a starting material to make all platform chemicals, okay? And the research and where we are with that, okay? So we do a lecture on that, and that is very interesting. You start with CO2, and you can make all the platform chemicals that you can make with oil, okay? And there's a lot of very exciting science being developed into using CO2 as a renewable material, So you take CO2, you make into compounds, and then you get CO2 back, capture it back, and then reuse it. So many crazy ideas are around, right? And we discuss a lot of them in class.
Yes, sir. But then, like, even if you, for example, develop a method to get CO2 into some usable products, first of all, just like extracting that CO2 out and concentrating it, that will be a first problem.
It's again energy intensive. Why? Because
Yes,
entropy, there's a penalty of entropy, right? Once you concentrate something, it's all thermodynamics, okay? Now, how do we get the energy? Could we have a very efficient? So it again comes up with energy, right? Can we get a clean source of energy? Then you can easily concentrate that, right? So it all ties down into energy, as you will see, as we will talk in our class. You will see that it will all tie down into getting a very clean source of energy. Okay, imagine what the nature does. It takes a diffuse sunlight and makes oxygen out of water. Oxygen is a very thermodynamically stable molecule. Oxygen with its unpaired electron is a very reactive molecule. Reduction of oxygen to water is one of the most enthalpically, one of the most exothermic reactions you can ever imagine. And that's what runs life. We got to find something similar. We got to find a leaf which does the same thing, but not with silicon solar cells, but with something else.
But then again, like, okay, Abel, go on, I guess.
Yeah, go ahead, Abel.
Thank you. So, sir, similar to what you had just said about photosynthesis, I've seen online about how they're actually making artificial leaves by 3D printing and things like that. So, is that also feasible anytime in the near future?
Of course, it is feasible. But the point is, right now, if you look at the artificial leaf, and if you do again what we call the life cycle analysis, right? What you need to get those compounds to make the artificial leaf, maybe it will be more energy intensive, that we make probably more CO2 than what we would by burning coal at this point of time. But that is how science changes, and you would be surprised at how fast science is changing, how incredibly fast things are coming up. So it just requires, that's how science progresses, right? We have to find a technology which is going to be much more, end to end, is going to be less polluting, less CO2, less energy intensive into doing it. Currently it is not, but it is going to be there. Okay.
Okay, so on the photosynthesis thing, so I read somewhere that Rubisco is actually a very inefficient, a very slow enzyme in the conversion, and then so even if we do have artificial leaves based on that same catalyst, wouldn't that also we'll have to the scale required for it, and then so building up things of that scale would itself be a energy as well as a material crisis in itself.
Absolutely. So it is going to be a material crisis, right? So the amount, so these are all numbers which we show in the class, that if you have to get, so suppose we have to get everything by our solar cells, right? The amount of silver you need, you're going to run out of the silver. Okay. So the question is, it is going to be a mixture of many things. One, it is going to be a mixture of renewable energy. For example, wind. Okay. In Germany, 70 to 80% of the energy comes from wind energy. They have extremely good technology for wind energy. India also has a little bit of the hydro, in the hydrothermal plants, right? So there are ways. It has to be a mix of many things, and we would talk that we teach that. And if you're interested, I can share, those who are interested, I can share maybe last year's a few lectures, and you can see those. We have talked about some of these issues. You need a mix of many things. Not one issue is going to solve it. Okay, but at the end of the day, what I'm trying to tell you, we need to be responsible. We need to consume less, okay, than what we are. Imagine I'm sitting in my room. Okay, I'll tell you. I'm giving all this big lecture of sustainability. I'm sitting in my room with my AC on. Okay, to just cool my whatever surface area of my body. I don't know how many meters square of my body surface. Okay, I'm cooling down the entire room. Okay, all the furniture. And this electricity which is coming is generating CO2. And that electricity, while it's being transmitted to IISER Kolkata, I think 30 to 40% is getting lost. And from that, I am cooling the entire room. Okay, just only to cool my own body. That's how inefficient we are. Okay, at the end of the day, it has to be us. Okay, we also have to consume responsibly. Okay, and that, there's no getting away from there.
That's a very good point, sir. Also, as again we discussed the biofuel thing in the sort of presentation.
Yeah.
And I can read somewhere that in Netherlands, I guess there are this multi-storage. They've developed this multi-storage this agriculture sort of a thing. So they grow stuff at multi-storage, and then I also studied that
Singapore also.
Yes,
yeah.
Yes, and then I also studied that actually they don't need to use a lot of fertilizers and things of those sort as well.
So these are some of the most important ideas, of that. How do you get phosphates and nitrates? These are the two important things. Okay, phosphates and nitrates. How do you make it in such a manner that most of it is not washed out? What is currently happening is that whatever you're putting in, most of it gets washed out. Okay, and only a little bit is being consumed by the plants. So we are very inefficient. Okay, so you have to find better ways of it, but it has to be an economical way, right? That's where either the government has to subsidize it, or we have to find, we don't need to always depend on the government. We have to find better ways of doing this to make it more efficient. And there are countries which are looking into it, and there are several people who are working on these different issues. And this is a mix of many things, chemistry, chemical engineering, agriculture, right? All of these are together. That's what it makes this problem so exciting.
Yes, sir. So yeah, I guess we are late already. So if anybody has any concluding remarks or anything, please go on with that. Otherwise, we can probably just conclude the event.
Yeah, I'll just like to say in the end that putting to like absolute trust on science and ignoring policy can also do equal harm, because the policy currently, as I also said in my earlier whatever I said, was the current policies are really not enough to slow down the problems of unsustainable future that we currently have. And that's why being scientists and people like us who are more knowledgeable about the issues plaguing our world, we have to, I won't say take active part in politics, but at least engage in such discussions more and more, which would should also include discussion of how current policies work, and think about changing those also, because uh, as much as we try to ignore it, policy is tied to our daily existence, and only science can, of course, not save the planet. That's all I'd like to say.
Yes, thank you, Sumit. That actually comes down to a very beautiful quote, I guess, by Einstein, when he said that those who have the privilege to know also have the responsibility to act. And so I guess your whole statement boils down to that one sort of quote. So okay, maybe if nobody has any other remarks before we leave, let's all have our cameras turned on, and let's just have a commemorative screenshot. If if no, if you're all okay with it. Okay, I could not actually. I guess my internet connection is not very stable, so I can actually see a very few cameras turned on. So maybe if
I'll
one of
take
you
it.
can.
I'll take it.
I have
Yeah.
taken a photo.
Yeah.
Okay, thank you, folks. It was a pleasure talking to you. Okay, so thank you very much.
Thank you so much, sir.
Okay, if you
Thank you
need
very much,
more
sir, for accepting
information,
our
please
invitation.
feel free to write to me, and I can supply things to you. You have a lot of stuff.
Thank you, sir.
Okay. Okay.
Thank you so much.
Thank you, sir, for attending, and it was a really
Okay.
Enlightening session,
enlightening
sir.
discussion. To be honest,
Yeah. Thank you.
to be honest, I had no idea of sustainability, but yeah, after hearing everything,
Yes, sir.
it's
We had learned a lot today. We get
Yeah.
an idea.
Sure. Okay. Okay. Bye.
Thank you.
Thank
Bye.
you, sir.
Thank you, sir.
Yeah.
And then, yeah, in the meanwhile, if anybody wants to still discuss, you could still continue to do that in our Discord channel, I guess. So that's great. Bye bye.
Hello.
Hello.
So